everyone. This is Gengyu. Today I'm going to present you our work SparseCore, Streamline and Processor Specialization for Sparse Computation. So first of all, let's look at the background of our research. As you know, sparse data is everywhere. We have sparse tensor, sparse matrix, and even sparse vector. Also, the graph data itself is in nature sparse. Now let's look at our focus, graph pattern mining. Graph pattern mining are a group of workloads trying to find the subgraphs in large graph datasets that satisfy some application-specific structural patterns. An efficient method for graph pattern mining is pattern enumeration, which is used by current state-of-the-art systems. I will explain the pattern enumeration in this slide. On the left, there is a pattern we are trying to find, which is the triangle. In the middle, it is the input graph. We will next explain how to find the triangle in the input graph. On the right, it illustrates the steps of finding it. We are now looking for a triangle with vertex 2 and vertex 3. We will first access vertex 2 and vertex 3's edge lists. Here they are vertex 1, 6, and 7, and 4, 7. And then we will perform an intersection on the two edge lists, which would give us the result as vertex 7. Now we found a triangle with vertex 2, 3, and vertex 7. As you can see, the key step here is to perform an intersection on the two edge lists. We found that the bottleneck here is the intersection. When running this application on modern CPU, we found that this kind of index matching caused huge inefficiency. On the right of the slide, it is the code for intersecting two strings. You can see that there are a lot of branches inside this loop, which is the source of the inefficiency. Now let's look at the motivation part. One solution is to build a specialized accelerator. It is important to note that we are not trying to build another accelerator. We believe that a fixed accelerator design may not be flexible enough to exploit better algorithms. We found some graph pattern mining algorithms do extensive checks to eliminate unnecessary computation. These flexible and still evolving checking algorithms are hard to be supported by a fixed accelerator design. For example, a recent graph pattern mining accelerator, FlexMiner, is unable to support new optimization based on inclusion-exclusion principle that can accelerate pattern comping by up to 100 times in GraphPy. Also, we believe that our stream-based ISA extension, which is tightly coupled with CPU, can reduce data movement. Unlike those accelerators like GPU, which needs to transfer data from host to device and device to host, our SparseCore doesn't require such movement. For some applications, this may be critical for its performance. In SparseCore, we proposed a stream abstraction, as the edge list can be seen as a stream of keys. We believe that such stream abstraction is a balance of the trade-off between flexibility and specialization. We developed efficient architectural components to support the stream ISA. The novel ISA extension intrinsically operates on stream, realizing both efficient data movement and computation. Also, as ISA extension targeted for sparse computation, we avoided the problem of unpredictable branch, which I mentioned earlier. Now let's look at our ISA. First of all, let's talk about string. In SparseCore, we consider two kinds of string. The first kind is the key string, which is a list of keys, such as the edge list in a graph representation. Another kind is a key value string, which is a list of key and value, such as the pair of indices of non-zero elements and the value in a sparse tensor representation. We also propose some register extensions. They are called as string registers. They will store information like stream ID, stream length, start key address, start value address, stream priority, and a valid bit. Now let's talk about some instructions for initializing stream register. They are called as stream read and stream value read. They will initialize a key stream and a key value stream. The operands are general purpose registers containing start key address, also start value address for stream value read, stream length, stream priority, and stream ID. Now for computation. We have stream intersection, stream subtraction, and stream merge. They will perform simple computation on key stream, intersection, subtraction, and merge. The operands are input and output strings and a boundary. The boundary is used to stop the computation once it is reached. Also, we have another version of these instructions. The difference is that those with the suffix of .c, they would count the number of matched keys without writing them to memory. We also have instructions like the value intersection. It has operands of input streams and user-defined computation. It computes the intersection of the keys of two input key value strings, and then performs the computation on the values of the corresponding keys. Now, let's consider two key value strings. One has keys of 1, 3, 7, and the other has keys of 2, 5, 7. The intersection of the keys will be 7. Let's assume the computation is multiply and accumulation. The result would be 13 multiplied 2, which is 26. The computation here would be any reduction operation like max or min. For data accessing, we have an instruction called stream fetch. The operands are stream ID, element offset, and the return key value. It performs the stream element access. When the offset reaches the end of the string, the instruction will return a special end of string value. We also have an instruction to deallocate a string, which is called as stream free. It will free all the resources related to this string. Now let's look at some code example. Here it is the code for triangle counting. On the left, you can see the loop of integrating through vertex 1 and vertex 2. Inside the loop, it is the code for intersecting the neighbor of vertex 1 and vertex 2. And on the right, it is the assembly code with our new instructions. We will first use stream read to initialize two streams from the edge list of vertex 1 and vertex 2, and then use stream intersection to perform the intersection. And finally, we will use stream free to release the stream. Now let's look at another example, multiplication of two key value streams. On the left, it is a code for matching the index and perform multiplication. On the right, you can see that we will first use string value read to initialize the two strings. And then we will use string value intersection to perform the multiplication. As you can see, all those branches are replaced by our string instructions. Now let's look at the architecture of SparseCore. First, for data accessing, we have scratch pad and stream cache. Stream cache or Scache will be used to fetch data from the cache hierarchy and store it like a cache. Once a stream read initializes a stream, stream cache will allocate a slot and start prefetching the data. Scratch pad is designed to store the intermediate data. Now let's talk about stream information. We have a stream mapping table, which will keep track of the mapping between stream ID and the hardware resources. And the stream register will hold information for the streams. For index matching, we have a dedicated unit called as the SU, short for stream unit. As for value computation, the stream unit will send the matched index to this value computation units. We have a value address generator, which generates the value address for the matched keys, and the value buffer, which is used to hide the latency of fetching value data, and also stream value processing unit, which will compute the value and accumulate it in the accumulation register. Now let's look at our evaluation. First, the simulator and configuration. Our simulator is based on this theme. We implemented SparseCore on it cycle accurately. And on the right, you can see the table of our configuration. And for the hardware cost, we implemented the key components of SparseCore, including stream cache, stream unit, stream mapping table, and stream registers at Chisel. The total area of our stream cache with 12 slots for stream unit, stream mapping table, scratch pad, and stream registers takes 0.73 square millimeters. In comparison, the area of an Intel Skylake server core is close to 15 square millimeters. Now, in this slide, the breakdown of the cycle for CPU and SparseCore with different datasets and graph pattern mining algorithms are shown in the two figures. We can see from the above figure that for CPU, branch misprediction cost takes a significant proportion of the total cycles. This is due to the code pattern of intersections, which contains difficult to predict branches. As shown in the below figure, for SparseCore, the branch misprediction cost is significantly reduced, which is due to our specialized instructions. The computation categories are counted as the summation of cycles when any functional unit of the CPU is busy. This category can be further divided into two parts, the computation and intersection. The intersection represents the cycles when the CPU or stream unit is executing an intersection or subtraction operation. The other computation category includes cycles for all other computation. Now, on this slide, it shows the results with different number of stream units. Each of our SparseCore has several stream units that can work in parallel. When the number of stream units is no more than 4, increasing it will generally improve SparseCore's performance. However, with more than 4 stream units, adding more stream units introduces significantly less benefit. On this slide, the figure shows the performance of SparseCore with aggregated stream cache and scratchpad bandwidth, varying from 2 elements per cycle to 64 elements per cycle. Increasing aggregated bandwidth can improve SparseCore's performance. However, there is a point of diminishing return. For graph pattern mining, SparseCore outperforms AutoMine on CPU by on average more than 13 times. SparseCore also outperforms 2 graph pattern mining accelerators, FlexMiner and TriJax by on average more than 2 times and more than 3,000 times, which is mainly due to our algorithm improvement. As for tensor computation, SparseCore also outperforms CPU significantly. So finally, as a conclusion, SparseCore extends the instruction set architecture to make stream first-class citizens and accelerates sparse computation with a unified architecture. We developed the SparseCore architecture composed of specialized mechanisms that efficiently implement the stream assay extensions. The result shows that SparseCore outperforms the recent specialized graph pattern mining accelerators and achieves decent speed-ups on tensor computation. Thanks for listening. Any questions?